actual components inside the processor in logic sim. So the first part is to understand, okay, that's really the core of the processor. Okay, those are the components. So once we know that there are the components, then the next item is going to be the microcode in the ROM. Each location in the ROM is what I call a slice, because each location in ROM specifies how components of the processor should connect to each other at a particular instant of time. So that's why I call it a microcode slice. The term microcode means it is a subpart or a component of quote-unquote code. In this case, it's referring to opcode. So a microcode is one particular component of an opcode. It is used to implement opcode. So microcode implements opcode by coordinating components in the processor to establish pathways between the components. Okay, so that's the second component. The third component is the RAM itself. So the RAM component in the processor is where we store data and also where we store opcodes. So opcode is basically the program that we are writing. Okay, so for the rest of this class, what we'll be doing is to specify the content in RAM for the most part, so that we can actually write programs, in this sense. And then you can write opcode in a very manual way. In other words, you can refer to the opcode table, which is a spreadsheet for documentation purposes, or you can also refer to the assembler manual. Both of these will describe what the opcodes are, what the binary bit patterns are, and so on and so forth. Which means you can, if you want to, specify the zeros and ones of all the opcodes, and write a program that way. But it's extremely tedious, if you were to do it that way. I can do it like a few times just so that you can see the process, but it's very, very tedious. And not only will you get tired of doing it, but it's also very prone to human errors, which means it's not really the best way of writing a program. So that brings us to the last component of tax toy processor toolchain, which is the assembler. The assembler is implemented in the form of a spreadsheet, as a Google spreadsheet. So with the assembler, you can write, instead of writing opcodes in zeros and ones, you can now write code in mnemonics. So mnemonics are basically things that are easier for people to remember, like no-op, N-O-P, is easier to remember than 00 in hexadecimal. Halt is easier than 01 in hexadecimal. Add is easier than the entire family of opcodes corresponding to the add opcodes. So the assembler will take the mnemonics and it will convert the mnemonics into actual opcodes, and they will give you a file that you can download, and then you can re-upload that file into LogicSim, into the RAM component, and that's how you can specify a program in the RAM component of the processor. The other part of the assembler that is really useful is to keep track of locations of opcodes and other things in RAM. So this way you don't have to keep counting, okay, where is this location? Because in order to specify a jump instruction, or to specify the location where you're going to grab content in RAM, you need to know where it is. But where a particular byte is depends a lot on, well, how long is the program? Every time you add additional opcodes into the program, it's going to offset everything else. So if you were to keep track of the count of everything manually, that's going to be very tedious. And you're going to make a mistake at somewhere along the line, and then your program doesn't work anymore. So that's what the labels are for. The labels are symbolic names of locations, so that you don't have to count 1, 2, 3, 4, 5, 6, 7. Oh, is that location 8 or 9? Okay, because it's just a symbolic name. It's much easier for you to remember and also to refer to symbolic names. So that's what the assembler is. So these are the major components. So when it comes to studying, in other words, when it comes to preparing for exams, and also to get an understanding of toy processor, where do we start? Okay, that's a very common question, I understand. So we start with the body of the processor. In other words, we start with the individual components. What is a multiplexer? Do we understand that? What is a demultiplexer? What is a register? What is a wire? What is a splitter? What is the RAM component? What is the ROM component? How does each one work by itself? So that's the first level of understanding that we must have in order to quote unquote study the toy processor itself. Is that okay? So once you understand the individual components, then the next question is just having a general idea of how things are connected. Okay, so you just look at the processor itself. I know it looks like a big mess, okay? But using LogicSim, using the Poke tool, it can help you quickly locate, oh, so this thing actually connects to all of these other things. Okay, so interactively, using LogicSim, you can explore the connections a little bit faster than looking at a picture of the processor in a static way. So once you understand all the components, how they work individually, where they are in the processor, then the next thing you need to study would be the instructions. So when I say study the instructions, I really just mean go to the opcode table or the assembler manual and just kind of look into the mnemonics and study the effects of each instruction. Okay, so it's not about the implementation of the instruction so much as it is just to understand, oh, the LD instruction is going to one particular location in RAM, grab the content at that location, and then store that into a register in the register bank. How does it get the job done? That's secondary, okay? We'll figure that out later, okay? But the first part is to understand what they do. So that's why in the second paragraph, it starts with, for each instruction, read the effect and think about what parts of the processor needs to be connected in what way to get a job done. So I'll give you one example here of the add instruction, okay? But the idea is you go through all of those instructions and you think in your head, okay, how do I get this done? So you basically circle the components in the processor, in the architecture, and you go like, okay, this needs to connect to that. How do we make that pathway possible? Well, it's only a matter of enabling, disabling the multiplexers, demultiplexers, putting in the correct selection bits into the multiplexers and demultiplexers, and so on. So then it becomes just a matter of how do we make all those connections. Think of yourself in a maze, okay? You're in a room, you need to go to a particular other room, okay? So you can study the hallways, okay, the paths and whatnot, but imagine there are doors, okay? So now the question is, which door needs to open, which door needs to close, and so on. That becomes the next level of question that you have to answer for yourself. So once you understand how the components should be connected, which I will go through a few times in class as well, then you have already understood the microcode, because the microcode for the most part is doing exactly that. All it is doing is to specify the control bits and the selection bits of the multiplexers, demultiplexers, and other various components. Is a register enabled, and so on and so forth. Is the RAM enabled, and so on and so forth. So once you understand how to do it manually, a microcode slice is really just zeros and ones to specify exactly the same thing. So the mystery of microcode should be gone. what it's going to do is it will evaluate the right-hand side, which is ID in this case. It's a symbol, which means it's going to resolve to a number, which is basically an address. And whatever that thing resolves to, it will be stored into the register, which is quote unquote the left-hand side. So for the instruction that is highlighted, A, register A is the left-hand side. In other words, it really literally means the same thing as A equals to ID in C and C++. Okay? So the next one is literally B equals to ID. And then we have L0 as a label definition, which means the symbolic name L0 is the address of the INC B instruction, the increment B instruction. Okay? Increment B literally just means, guess what? Increment B. What does that do? B is, yeah, go ahead. Add 1 to B, exactly. So it's going to, B is just going to be incremented by 1. And then we have another LDI instruction. So this the next instruction, LDI C, comma, ID end, ID underscore end is another label down there. So all it's doing is it's loading the address represented by that symbolic name into register C in this case, and then we'll do a compare. Okay, compare we haven't really talked about yet, so we'll talk about the compare instruction. And here's the opcode table. So you might want to print out the opcode table because it is going to be helpful. You know, it's a very quick way to look up instructions and figure out what they do. So this time we are looking up the compare instruction. And let's see, we'll scroll down to pick up the compare instruction. There we go. So here's the compare instruction. And let me zoom in just one level, because 2 levels is a little bit too much. I lose column D if I zoom twice. So zooming in once is enough. So here's the compare instruction on row 35. And what does it do? Well, if you look at column C, it literally describes what we're doing with the registers. It's going to do a subtraction, x minus y, but it doesn't store the difference. If you look at the subtraction instruction, SUB, it actually takes the difference and stores it back into register X, whatever register X is. This one doesn't do any storing. So all it's going to do is to go through the motion of the subtraction, set the flags, or clear some of the flags, and that's it. It doesn't store the actual result. So the compare instruction is just like a subtraction, except it doesn't store the result. It just changes the flags, and that's it. Okay. So switching back to the code. All right. So we're done talking about this one. So the next instruction, there's no such thing as JXI. So that X has to be changed. There are 5 options to specify that X. Those are the 5 flags. The instruction here will tell you which 5 flags we are talking about. This is a conditional branch. A conditional branch means it will jump to L1 if and only if whatever the X flag is set. So if X is C, it means we will only continue execution at L1 if and only if the carry flag is a 1. If the X is, let's say, Z, okay, that means we will only continue execution at L1 from this instruction if and only if the Z flag is a 1, and so on. All of those flags are affected by the compare instruction. Is that okay? More or less? Okay. Moving on. So if you do not branch to L1 because of this instruction, that's okay, because the next one is an unconditional branch. JMPI is unconditional, which means when you execute JMPI, whatever label is after that, it always goes to that label. In this case, it's L2. So that means JMPI L2 is always going to continue execution at the label L2, or I should say the instruction right after the label L2. Is that okay? Same thing as a goto in C and C++. So JMPI is equivalent to goto in C and C++. Is that okay so far? All right. And then we got, no op, which we understand already. Another JMPI instruction, another no op. Here's increment again, okay? We're just increasing the value of a by 1. JMPI to L0. L0 was all the way up there. This is a loop, okay? Because we're continuing execution, unconditionally going back to an earlier part of the program. This is how we can make loops in assembly language programming. And then here's done and a halt instruction. The halt instruction does what? It's an instruction that never ends. It keeps kind of in an infinite loop. Okay, so when you get to the halt instruction, it's really obvious. So you can stop clocking the processor and you can get the results. And here's ID, which is a label definition. And then we got some byte instructions here, or byte operatives. So each one is reserving a byte and initializing that location with a value of 0. So what this is going to do is to reserve 7 bytes, and in each location that it reserves has an initial value of 0. But you are going to replace all of these with digits from your student ID when you do this homework assignment. So this is going to be the rightmost digit of your student ID. The rightmost digit is also known as the least significant digit. The last one is going to be the most significant digit, or the leftmost digit of your student ID. So when you run this code, you have to remember, when you assemble this code, you have to remember to replace all the bytes with your student ID, digits from the student ID. Is that okay? All right, so I gave you an overview of what this program is going to do. So the key of this homework, or this particular step, is to count the number of execution of a particular instruction. Okay, so here. So your task is to change JXI to one of the 5 conditional branch instructions so that the no-op instruction of L2 execute the most number of times before the program reaches the halt instruction. So there are 5 variations. Okay, I'm going to write it on the whiteboard here. So you have JCI, JZI, JSI, JOI, and then JLI. So these are the 5 variations that you can use in place of JXI. Depending on which one you use, the number of times that you execute the no-op instruction right after label L2 may change. So you want to come back and say which instruction gives you the most number of times of executing the no-op instruction at label L2. So going back to the code, let me just highlight, which instruction are we talking about? We're talking about this no-op instruction here. So you need to somehow count the number of times this no-op instruction executes. But you can also try to understand the program itself and use an analytical way to figure out the number of times for each variation of the conditional branches. So it's up to you. You can do it one way, you can do it the other way. Is that okay? Are we okay? Yep. Okay, so JXI, well, I can do the explanation, but I can explain it using the spreadsheet. Exactly. So the spreadsheet, which is the opcode table spreadsheet, that's the easiest one to refer to. So when you look at the JXI, JSI, JOI, instructions here, so we are focusing on this entire series of mnemonics. So we'll look at the mnemonics first, and then we can potentially look at how they actually execute. Yep.
Could I create something and then implement it right after that line of code?
You cannot change the program. You're not allowed to change the program. So I'll teach you how to do the counting. Okay, it's not that hard. So, but this is the documentation of the conditional branch instructions. So we got JLI, JOI, JSI, JCI, and JZI. They all look about the same, right? The only difference is what letter do we specify corresponding to a flag that a register that our processor can handle. Okay? Is this understood? PC equals to L question mark, whatever the program counter points to, colon, and then program counter plus 1. It's a ternary operator. So how many people still remember the ternary operator? I think we used it in this class. Okay. So the first one, which is L, is considered a condition. So it's either true or not true. Okay. So if L is 1, that means it's true. If L is 0, that means it is false. If the condition is true, then we evaluate whatever is in the middle. That becomes the value of the expression. If L is false, or if the first expression is false, then we evaluate the third expression and use the third expression as the value of the entire thing. Okay, so that looks kind of awfully confusing. What is the program counter pointing to? Why are we retrieving whatever the program counter is pointing to? Remind me again what the decode cycle does when we execute an instruction. We just talked about it earlier today. So what does it do? The decode cycle, it has two things to do. One is to copy the instruction register to the microcode pointer and pad 4 zeros. Okay, that's one. What is the second thing? The second thing has to do with the program counter. What does it do to the program counter? It increments the program counter. So that means by the time you get to the execute phase of an instruction, the program counter is already pointing to the byte that is 1 after the opcode itself. So that means you basically just need to specify the location that you want it to branch to as the second byte of that opcode when we specify a conditional branch instruction. And it will go there if the flag is set. What if the flag is not set? What if the flag is cleared? Then the program counter will increment one more time because it has to do that to skip the location that actually specifies where to go when the flag was true. Is that okay? More or less? Or not? Okay. So let's say you go like, I have no idea what this is. Okay, what is this talking about? What are you going to do next? Let's not do the conditional stuff first. Let's go for the unconditional branch, JMPI, which is basically branching to I itself. Okay, which is go to I. Okay. What does it do? The program counter gets whatever the program counter points to. Okay, but wouldn't that just be going back to the same location? We'll do something kind of funky. What do you think? The program counter is already incremented in the decode phase, so that means whatever we are dereferencing using the program counter at this point is going to be the byte after the opcode itself. So, well, let's take a look. Okay, so the best way to understand the opcodes sometimes is not to stare at the description, but to actually make a program as simple as possible and then try to run that program and understand the mechanism. So I'm doing this for you, okay, so that you know what to do when you encounter another instruction that we haven't seen before, but the description is here. So how do you design an experiment of your own to understand the instruction? So we go to the assembler, go to the source tab, and we try to specify a program as simple as possible that makes use of the jump instruction. Okay. I think this may be one already because this is coming from the Monday, Wednesday class. Yep, okay, well, this is it. So the source tab, okay, let me go back to the source tab here. So the source tab shows you the code of the program. It has one single JMPI instruction going to label L1. L1 is defined here, which means L1 is really the symbolic name of the address of the halt instruction. The no-op instruction in between, they're only here so that we can specify, so that we know that L1 is going to be at some location. Is that okay? So now, if we don't have the assembler, then you have to convert the mnemonics into the actual opcode manually, which is really cumbersome. But since we do have the assembler, we can kind of look at the assembler and say, and ask the assembler, what does it look like? Okay, what does each instruction, what does each line translate to? So that's what the assemble tab is really useful for, is it shows you how each line is processed. And particularly, we pay attention once again to column W, X, and Y. Column W are the addresses, column X is the first byte at that address, and column Y is optional. Sometimes we have a second byte to specify. All right, so if you look at the first row, JMPI L1, you can see that it is at location 0 because it is the very first instruction of the entire program. We always start from location 0. So the fact that the JMPI instruction is starting at location 0 should be no surprise because we start at the beginning of the RAM locations. The opcode itself is a 40. Okay, you can look up the opcode table. It will show you that the opcode of the unconditional branch is 0100 and then 0000, which corresponds to 40 in hexadecimal. But it has 2 bytes. The second byte is 04. The 04 is specifying where are we going? Well, we're going to location 4. This is an unconditional branch. We're going to location 4. Why are we going to location 4? Because location 4 is where L1 is defined. L1 is defined here, which means it is the symbolic name of the byte that is after that, which turns out to be the halt instruction. Why is the halt instruction at location 4? Well, because we have to do some counting. The first instruction, the JMPI instruction, takes up 2 bytes. 0, 1, and then we have 2 no-op instructions, 2, 3, and that's why the halt instruction is at location 4. If we did not have the assembler, then you will have to do that counting yourself to figure out, oh, I see, location 4 is where I want to branch to. But because the assembler does have your symbolic name or labels, it can figure that out for yourself, for you, so that you don't have to keep track of the count. Is that okay? Does everybody understand why the JMPI L1 instruction has 40 as the opcode and then 04 as a second byte to specify where are we going? Yes? Okay, very good. Yep.
The 04 is constituted by the L1, right? So if I change L1 to L3 or something else, the number will also change to that location.
If you have a different label definition for L3 and whatnot, yes. If you insert one more no-op instruction in between, then that will also change the definition of L1.
But the 40 will not be changed because it is the opcode for the job.
Yes, that is correct. So the 40 does not change because 40 or 01000000 is the binary representation of the jump instruction. Yep, so that does not change. All right, so are we good so far? Okay. So now we go to the RAM file tab to download the program. So we say download as, and I always use CSV for this purpose. And we'll say this is my JMPI and leave the other one around. This is the second one. Huh? There's no audio? Okay. Huh. Okay, so it is being streamed again. Yeah, I've just restarted the stream. So does it have audio now, or you have to give it like about 15 to 19 seconds because there's a lag. You're getting audio? Okay, thanks. That's kind of cool. I mean, you can just kind of test it like right away. All right, thank you for testing it. So getting back to here. Okay, so we have the RAM file, and then I have to restart Logisim. So let's go ahead and say, and then we go to the processor. Oh, cisp310 processor. There we go. Okay. And we go to the RAM component. We say load image, and we're going to load the image that we have just downloaded. I call that jmpi.csv. So now we got this really simplistic program loaded here. And remember what I said, if you want to understand how the processor works, it's best to single clock the whole thing using Control T. But before you do a Control T, it really is also a good idea to look at the ROM component first. We are now doing the fetch cycle. Now the fetch cycle we have talked about at least once or twice already, so it really should be kind of no big surprise, but we'll do it anyway. The first thing that the clock cycle is going to do is to grab the instruction and put it into the instruction register. So that's why the instruction register now has 40, because that's the opcode at location 0. The second thing it's going to do, which is the falling edge, is the microcode pointer itself, which is this one, is going to increment. That's the only register that is sensitive to a falling edge. Now we are decoding. So when we have a rising edge on a decode cycle, two things is going to happen. One is the microcode, on the rising edge, one thing will happen, which is the program counter, which is now 0, 0, is going to increment to 0, 1. The second thing that's going to happen when we have the falling edge is the microcode pointer is going to be almost the same as the instruction register, except we have one extra 0 padded on the right-hand side. So those are the two things that needs to happen on the rising edge and falling edge at this point. So Control T is the rising edge. We should see the program counter incrementing from 0, 1, 0, 0 to 0, 1 right there. And then now we have the falling edge. So at the falling edge, the microcode pointer should be 4, 0, 0 because it's copying the byte onto the most significant 8 bits of the microcode pointer, but the least significant 4 bits are just padded by zeros. So that's why, on the falling edge, the microcode pointer should now be 4, 0, 0. So Control T one more time, and now we are decoding, and we now get to location 400, which specifies the first microcode slice for the JMPI instruction. Are we good so far? So the key is, where is the program counter pointing to? The program counter is pointing to location 0, 1. Do you remember what is at location 0, 1? Huh? No. At location 0, 1, which is the byte right after 40, is what? 0, 4, exactly. So the program counter is pointing to a location in RAM that has a content of 0, 4. 0, 4 also is what? How does 0, 4 relate to label L1? It is label L1, okay? Which is where the halt instruction is, which is where we want to go. So now the question is, how does the processor grab the content at location 0, 1 and put it back into itself? That becomes the question. But when you look at the component itself, we can see that the RAM component is active because it is selected. We know it is a read operation because LD is a 1. Okay. Now, who's specifying the address? So you have to go back to the multiplexer. The multiplexer has a 1 as a selection, which means input 1 is controlling the address port of RAM. And that turns out to be coming from the program counter. So the program counter is telling the RAM component which location to access. And the RAM component is active, doing a read operation. So then the next question is, okay, so the data has to go somewhere. Okay, so where's this going? It goes to many places, but one of the places that it does go to is this multiplexer. This multiplexer has a select of 1, which means input 1 of this multiplexer becomes the output, which goes into another multiplexer, but input 1, the selection is also a 1, which means input 1 of this multiplexer becomes the output. Oh, that goes straight back into the program counter. So the program counter has an input of 0, 4. The output is 0, 1 at this point, and it is enabled. You can see the program counter enable is a light green wire, which means on the next rising edge, the program counter is going to be updated to 0, 4. So let's do that. Okay, Control T, and you can see how the program counter is now changed to 0, 4, and the microcode is going to be. This is the last. This is the only slide in terms of the microcode. So the microcode is going to microcode pointer is going to increment to the next location, but the next location is going to be 2 and then followed by all zeros. Do you guys remember what that's going to do? It's going to reset the microcode pointer, okay? Which means the microcode pointer is going to go back to 0, which starts the next fetch cycle to fetch the halt instruction. Okay, so this is the kind of quote-unquote studying that I want you guys to do, is really to design very simple programs, okay, not complicated, focus on one particular instruction, and actually see what the processor does. Okay. Now, I understand, I can go through this in a few minutes, okay? But it might take you a little bit longer because you're not as familiar with the processor. And so it might take you a little bit longer to figure out, okay, which component is active with this particular slice of time. It will take you a little bit longer. But the more you do this, the faster you will get familiarized with the processor. And then the understanding of the next instruction is going to take less time. So it's kind of an exponential thing where the initial learning curve is kind of steep, and then as you go, it gets shallower and shallower. But without going through the first steep part, there's no way to get to the later part that you will need in order to succeed in this class. Is that okay? So I can help you with this process by pointing out what you need to do, but I cannot do the learning part for you, because I cannot mind meld like a Vulcan. Okay, so that's the part that you kind of have to do, is to go through these experiments and try to understand, how the whole thing works. All right, so this one explains. Okay, so we'll go ahead and actually do it. So the falling edge is going to turn the microcode pointer back to 0, Control T, and now is the next fetch cycle. It's going to fetch the halt instruction. So now the rising edge is going to change the instruction register. The instruction register will change to 0, 1, which is the halt instruction, the halt opcode, like that. And then the falling edge is going to do the increment of the microcode pointer. So the microcode pointer will point to location 001, like that. This is the decode/program counter increment phase. Yep. Okay, so that's a very good question. There's no way to step backwards. However, OBS is an open source program, which means when you are doing this, record yourself. So that way, you can go like, okay, what did I just do? What changed on the screen? Stop that, recording, and then replay your own, videotape as you go through the experiment. Question? Okay.
After it's a little bit less setup.
Okay. Okay. So QuickTime for Macs. OBS is open source, so you can get it on Linux and Windows, and also Mac OS 10. I think Windows may have its own built-in screen recordings utility. I don't know for sure.
It does now called Game Bar,
Okay.
but it's mostly just for gamers.
Okay.
Yeah. Hit Windows G, it'll bring it.
Yeah, OBS works really well. You don't even need to have a YouTube account to use OBS because with OBS you can start recording instead of start streaming. So that would just record to an MP4 file or something like that. They can replay using just about any tool. VLC can actually do the audio. So I don't VLC because I want to record the audio as well in the class. But if you just want to record just the screen, VLC can do it as well. So VLC can record and play back, depending on how you configure VLC. So you got some tools like that, and after a whole session, you say, okay, this is useless. I don't need to play back the audio, the video. You can just go ahead and delete the video. It doesn't take up that much space. In the good old days when you only have, like, 1 gigabyte for an entire hard drive, yeah, this is a little bit costly. But these days, you guys all have 1 terabyte, 2 terabyte, 3 terabyte hard drives. So this is a drop in the bucket, to record a whole hour of you experimenting with the toy processor. Right? Yep. So you have tools that I never had when I went through college. Okay, so that is that. What time is it? Okay, we have about half an hour left. So we'll go ahead and look at another program as an example of, but how do I know how many times a particular location has executed? Okay, because that's one of the things that you have to do. So once again, we go to the source here, and this time we'll change the program to something else. Okay, so we'll go ahead and delete this code here. Now remember, whatever you're deleting, do not delete anything other than column A of the source tab, okay? Because everything else has formulae, and you don't want to delete the formulae. So let's go ahead and write another program here. So I'm going to do a LDI B with, I don't know, 87, LDI A with 12, okay? And we have label L1, L0. Okay, this is L0. And then we'll do a compare, CMP BA. And then I'll use J CI to label L2, L1. Doesn't matter. Okay, I'll fix that later. And you can see that if you use the spreadsheet to write the program, it will give you error messages as you write the program, because label L1 has not been defined yet. Okay, it's going to be defined later on. But that's okay, because I'm not done with this program yet. And then we'll specify a no-op instruction here. And let's say we want to count the number of times this no-op gets executed. And then we'll go ahead and decrement B. And we'll increment A. And then do an unconditional branch back to label L0. L1 is defined here, and here is my halt instruction. So that's my entire program. Okay. At this point, I'm not too concerned about you understanding the control structure of this code. All I want to focus on is, so how many times are we going to execute the no-op on row 6 of this code? That's my only concern right now, because your program for this lab has to do about the same thing. Okay, so I just want to focus. Question? No? Okay. Yeah. No, not you, but oh. Yeah. Oh, no. Okay. Yeah, because when people kind of do that with the pen, sometimes I misinterpret it as having a question. Okay, so let's run this program and figure out something. Now, we can always just go to the RAM file and download this program. Okay, so we'll go ahead and download this code as I'll call it count. Okay, we just want to do some counting. And then we go back to the processor. Now, when you want to reload with another program or restart the same program, my recommendation is do a Control R to reset the whole processor, which will automatically clear the content in RAM. But that's okay. You just right-click on RAM, click Load Image, and specify what you're loading again. This will make sure that you don't have anything left over from the previous time you used the processor. Okay, so it's always a good idea to reset the processor using Control R. All right, but before I run this program, I'm going to set up a few things. Okay, so this is the kind of trick that you probably want to use when you're doing your lab. Go to the Simulate tab or Simulate menu, and this time we want to set up some logging. So go to the logging part of the Simulate menu item. And now we have a smaller window. It has 3 tabs. Selection is one of the tabs, Table is one of the tabs, and File is the last one. Selection tab allows you to select what do I want to log. In other words, if the simulator observes any changes to whatever thing I select, it's going to have a log entry in either the table or the output file. Typically, the most important thing that we do have to log would at least include the program counter, because the program counter is going to tell you where we are executing in the program, and that is always useful. Okay? But you can also include some additional stuff. Okay? For instance, you can include any registers in the register bank. Okay? We can go ahead and do that, because we want to kind of figure out what is happening to register A and what is happening to register B. Okay? You can also go log some of the other entries. Depending on what you're doing, occasionally you might want to log the microcode pointer, but that changes a lot of times, which means you're going to look at a lot of log entries, which may or may not be helpful. Okay, because you might want to focus on only a few things. In this case, you know what? I'm just going to log the flags as well. Okay. Now, the next thing you want to do is to figure out, okay, are these things being logged using the base that you want? The program counter is now logged in base 2. It's binary, which is not the ideal base to use, because it's just going to give you a lot of digits. So you can change the radix by clicking this button. Now it's base 10. It's okay, but I think it's best to log it in base 16. The register bank stuff, we're logging in base 10, because we are really just looking at some values and comparing those things. The flags register, we'll keep it in base 2, because with the flags register, I need to know what is each individual thing. So that means I do need to know the zeros and ones for each bit positions. So binary is good for the flags. Okay. So now that we have set up all the things that we want to log, then table is, once you have logged certain entries, then table will show you, what it has logged. But that's not my recommendation. My recommendation is to use a log file instead. So if you want to use a log file, you have to select a file first, which means you just need to say, okay, what is going to be the output file of this log? So I'm going to specify in the temp folder. We'll call this one count log.tsv. The extension is optional, but I highly recommend the use of TSV or tab separated value as an extension, because that's the kind of file it's going to generate. If you use the extension TSV and you double click, Microsoft Excel can open that file automatically, understanding that it is a tab separated value file. So that can really help you, in terms of visualizing the log itself. Okay? So I highly recommend the use of TSV as an extension, but once again, it's an optional thing, and you can always change that extension if you want to. Click Save. Nothing is happening right now because I haven't even started to run the program yet. So you can close the window at this point. And in this case, I don't need to do a Control T. I can just do a Control K. Control K means enabling the internal clock to tick by itself, so that you don't have to keep typing Control T on the keyboard. So I'm going to type Control K at this point, And you can see the program is kind of executing. I don't have a particularly fast computer, so it might go a lot faster on yours compared to this one. But now it doesn't seem to do anything right now. So let's go ahead and check a few things. The first thing I need to check is, now I can type Control K at this point to stop the clocking. I can see that the program counter is at location 0D. And where do you think location 0D is? What is at location 0D? It is not the halt instruction because the decode cycle increments. So 0D is one location past the address of the halt instruction. The halt instruction should be at location 0C instead. Okay? Let's check. So we can now go back to the spreadsheet, go to the Assemble tab, and then we locate the halt instruction. And indeed, you can see the halt instruction actually has an address of 0C, but the PC, the program counter, has a content of 0D because the decode cycle automatically increases the program counter by 1. So by the time we are stuck in the halt instruction, in the execute phase of instruction execution, the program counter is already 1 byte past the actual address of the instruction that we are executing. Is that okay? Now that might seem kind of trivial, but it is going to be important when we look at the log file. So now that the program is done, we want to take a look at the log file. So you can use a normal text editor to look at the log file. The most normal text editor is called Mousepad on a Linux system. And we'll just take a look at log count log.txv. And it's kind of look like this, because of the tab. It's kind of not really, easy to understand. Okay. But it really is easier, much easier, if you use a spreadsheet program to do it. So what do you think would be a good spreadsheet program to use? Huh? I use Linux. There's no Excel. There's LibreOffice, okay? But guess what? There's also Google Spreadsheet. You can have a Chromebook and use Google Spreadsheet to do this. So we'll use Google Spreadsheet. So let me go to the shared folder and make sure this is the shared folder of the right class, which it is not at this point. So we go to cisp310, shared, and I'm just going to go to examples to add this one. So we'll go ahead and add a new spreadsheet. And using Google Spreadsheet, you can do an import. So you go to File, and then click on Import. And you can upload with that import. And then specify the file that we were looking at earlier. And I think that's count log.tsv. There we go. All right, so now you're presented with several options. Replace spreadsheet is fine, okay, because currently the spreadsheet is blank anyway. Detect separator automatically will work, okay, because we're using a tab as a separator. This one, I would turn it off. Okay, convert text to numbers and dates, turn it off. Because what that would do is, if you have a bunch of zeros, it would turn that bunch of zeros into one single zero. It doesn't understand some of those numbers are in base 2, so it would interpret those numbers as they're in base 10, which is not good for our purpose. So I would turn off convert text to numbers and dates when presented that option. Okay, so we import data. And now we have the entire trace in the form of a table. All right, so this is the table. We have the program counter, the register bank. Okay, you can actually differentiate which one is which one. This is register A, and this is register B. And these are the flags. Now, if you want to understand which bit of the flag is which actual flag, you can go to the ALU, but if I remember correctly, this is the carry flag, the Z flag, I think that's the sign flag overflow and the L flag. I could be wrong, okay? But they're all defined in the processor itself. Go to the ALU component and look at the flags out port. That's basically where it is defined. Okay, so now we have the whole log. But remember, our objective is not even to look at the flags register. Our objective is to count the number of times the no op instruction has executed. So to get to that part, we go back to the assembler tab, assembler sheet, and then we look at the no op instruction, and we go like, this is the only no op instruction. It is at location 7. So now the question is, how do we know from the log that we have executed the no op instruction? What do you think it's going to look like? So we'll go back to the log itself, and let's see, that's not it. Okay, here's the log, and location 7. Okay, so the program counter is at location 7. The only reason why this entry shows up is because the program counter changed from location 6 to location 7. But that's only because this is because of the decode of the instruction before the no op instruction. So what we really should be counting is the transition from 7 to 8. Okay? The transition from 7 to 8 with the program counter is because of the decode of the no op instruction itself. So that each of those transitions represents the execution of the no op instruction. So now we just have to count the number of those transitions. But that's okay, it's really easy because 08 only appears once, okay? The execution of the no op instruction does not change the program counter any further. So you can just go ahead and count the number of 08 of this entire column A. That sounds pretty tedious to me too. Does it sound tedious to you? Maybe. Well, it depends on how long the trace is. If the trace has like 6,000 lines or 6,000 rows, I mean, that can be a little bit tedious. So now you need to understand how to use a spreadsheet. The Google spreadsheet has a lot of features, kind of same way as Excel or LibreOffice. There's a feature called COUNTIF. Okay, I'm not going to explain what COUNTIF is going to do because it has online help. Okay, just knowing the name COUNTIF is helpful already. So it says, okay, what range are we doing all the counting? Well, let's specify the entire column A. So we say column A here, okay? And then the next one is, what are we looking for? What counts as one more? That's the criterion. The criterion is a string that specifies what are we looking for? Well, if you look at the example, you're greater than 20. In double quotes, maybe this one is equal to 08. Does it make sense? Okay, because we are looking for rows, or we are looking for cells that looks like this. Okay, close parenthesis, press the enter key, 38. Well, does that make sense? For each iteration, we are decrementing B by 1, we're incrementing A by 1, and when B is less than A, we get out of the loop. That's what the JCI is doing, because C is also the same as B. Carry is and borrow are the same. Okay? So now the question is, how many times do we have to go through that loop so that register B will finally be less than register A? That's the question. So to get a rough estimate, okay, you're looking at 87 minus 12, the whole thing divided by 2, possibly have 1 added to it, depending on whether it's odd or even, right? So 87 minus 12 is 75, okay? So 75 divided by 2. 75 is a odd number. So that means if you take this number, you have to add 1 more in order for that to cross over. 75 divided by 2 is 37. and then plus 1 is 38. So the theoretical number does match the actual observed number. Is that okay so far? So do we understand, how to use the ability to log in order to answer those questions? Okay, now that we have done it once, okay, how do we reset the whole thing and do it again? So you can go here, go to Window, go to Simulate, go back to Logging, go back to File, okay? You can turn it off by disabling it, or you can just run the whole thing again and see what happens. Okay, so we'll go ahead and leave it alone, do a Control R, reset the entire processor, go back to the RAM, reload it, reload the whole program in. It's count.csv, and then we run the whole thing again, Control K again to stop it, and then we go back to the spreadsheet and see whether it has changed or how it has changed. It has got 781 lines. So we want to see if, okay, so basically every time you rerun the program or reset the processor, the whole file gets regenerated from scratch. How do I know this file is regenerated from scratch? Because I can look at the time. And it is just a minute ago. So that means this is a fresh file. It just generated this file. So every time you run the processor, it's actually, and when you type reset, it will reset the log file as well. It will start logging from the beginning again. So that's more reason why you should type Control R when you're done with one instruction. Let's say you're done with JCI and you're ready to test JZI, Control R, okay, and then change the program. Remember to reassemble the program and change that one location. The 5 variations is only going to change one single location. So you can either understand which location to change and change just that, so that you don't have to redo the entire thing, or go to that program and change that one instruction, reassemble, re-download the RAM file, and then reload it back into the RAM. So there are several ways to do it, and it's up to you to decide how you want to do it. Are there any questions about this part? Because I'm really just kind of showcasing, how to get this particular lab done. Yep.
I have a question. Why do you pick the one where you go from 7 to 8 when you count down on your spreadsheet?
Well, the spreadsheet is not really counting the transition itself, but the number of times your program counter is 08 is what I'm counting. Because the no op is actually at location 07, but the log is corresponding to 08 because the decode cycle increments the program counter from 07 to 08. So it is the number of times that the program counter becomes 08 that is actually significant. Any other questions? So here's my question. What are the chances that the no op instruction of your lab so happens to be 08? Probably not. So you have to figure out where is the no op instruction in your lab. I'm thinking it is probably not location 08. So are there any questions about the process, the tool, what is involved, when you have to do this lab? No questions? Let's see, we got 5 minutes left. That's a lot of time. Let's examine how conditional branch works. Okay? So let's go back to the assembler spreadsheet. We'll change the program again, this time to illustrate how conditional branch works. So we go to the source tab and go like, okay, this is not the program that we want anymore. And we just want to design a program so that we can test how conditional branch works. In other words, you want to set up a condition where the conditional branch is actually going to branch, and you want to set up another example where it is not going to branch. Okay, So I'll give you an example. So we'll do LDI register A with 0, LDI register, LDI register B also with 0, okay? Compare register A to register B. So at this point, which flag should be set? I subtract 0 from 0. Which flag should be set? The 0 flag, very good. Okay, so we'll do a JZI, okay? JZI to some label L1. And we'll put a halt here, which we should not get to, right? We should not get to the halt instruction on line 5 because we should have taken that branch to label L1. So here's label L1. And label L1, at label L1, I'll do a JCI to label L2, which should not branch, okay? Because this is off of the same compare. If you subtract 0 from 0, is 0 less than 0? No. If 0 is not less than 0 unsigned, or signed actually, then the carry flag should not be set. Remember, the carry flag is the same thing as the borrow flag. The borrow flag is set if and only if the minnow is less than the subtrahend interpreted unsigned. Where did we talk about this? Binary comparison, exactly. Okay. So this branch should not happen, and we should end up at this halt instruction here. And we still have to define the L2 here just so that we can get to it. So now we have set up a very simple program so that we definitely know that we will take the branch on line 4 and we'll definitely not take the branch on line 7. So when you execute this program, you can single clock at those instructions. So now we go to 3 more minutes. I think we're fine. Go to File, Download. Okay, I'll call this one Flags. Go back here, Control R. Remember to reset the processor every time you want to load a new program. And this is flags.csv, like so. Okay. And this time I'm only interested in the conditional branch instructions. So that means I don't really need to do anything until the processor is going to execute the JZI instruction. The JZI instruction has an opcode of 45. So I don't really have anything to do until the instruction register has a content of 45 in hexadecimal. Whoops, take it back. I think 45 is correct, but let me just double check. Yep, 45 is correct. There we go. So switch back here, and this time I'll just do a whole bunch of Control T's until the instruction register, this guy, is 45. Okay, so Control T. There you go. Okay, so now we are decoding the instruction of 45. It's now decoded. Now we have to stop and go like, okay, what is going on now? Okay, so we want to study what potentially can be changed. And the first thing you need to know, or the first thing you need to investigate when you want to understand what an instruction is going to do, is to find out what registers are enabled, because that usually will give you a clue of what else you need to look into. The program counter is enabled, which means I now need to know how the program counter can potentially be updated, which means I need to look at the input into the program counter and say, how is it connected? Well, it is connected to this multiplexer, and this multiplexer has PC mux being a 1, which means we are taking input 1 from this multiplexer, and that input 1 is ultimately connected to the data bus, which is the byte after the opcode. Okay, but now the next question is, how come PC mux is a 1? PC mux is not one of the direct outputs of the ROM. So something computes PC mux, so it becomes 1. So now we have to look at PC mux. Okay, you'll click on PC mux so that every PC mux is highlighted. Okay, this is not determining PC mux. So we want, oops, there we go. So PC mux, as it turns out, is the output of this particular multiplexer. This particular multiplexer is selected by PC mux because it's a multiplexer, it's a selector to a multiplexer itself. So PC mux, if you click on it, has a value of 0, 0, 1. 0, 0, 1 means it is taking input 1 to become the output. Where's input 1? Input 1 traces all the way back to the output of the flags register, same bit, bit 1. What do you think is bit 1 of the flags register? The 0 flag. How do we confirm that? We go into the ALU, we go to the flags out port, which is here, and we look up bit 1, and that's Z out. That's the 0 flag. How do we compute the 0 flag? We track it all the way back to Z out, this particular tunnel. It is the NOR gate of all the bits of the output of the ALU. In other words, because the processor is quote-unquote open sourced, you can track down every single wire of why it has a particular value. And that is how you study the toy processor, is to keep tracking things down until it is fully explained. Is that okay? I know it's not the same way that you study in many of your other classes, but in this class, that is what I'm expecting you guys to do. This is not a history class. So it's a little bit different when it comes to studying. All right, so we're going to transition to the lab. I will have it set up by the time we get to the lab so that you guys can get started.